So for this video, we're going to introduce the concept of line integrals. So in Calculus 2 and at the end of Calculus 1, we were introduced to integrals. And for the most part in those classes, we were just taking integrals of a function of a single variable over an interval from a to b. Or, for improper integrals, we might have gone from minus infinity to infinity or something like that. But in any case, we're only inputting one variable there. So there's going to be lots of integrals in this course where we're integrating over things that are not intervals and integrating functions that are more than one variable. So this is going to be our first case of this. So let's recall back when we were doing dot products, we generalized from the really basic physics of just work is equal to force times distance to saying if we had a force that's given by a vector f and we move it some object, a displacement vector of d, then we saw that the work was given by the dot product of the force and the displacement vector. So what we'd like to do now is we'd like to do a little bit more general here, and we're going to let our force be a vector field. Here I've written it with two variables x and y. We'll see there's nothing important about having two variables x and y. It could have more variables than that. So you can just think of this as a vector field with any number of variables in there, but we'll usually stick to 2 or 3 variables as we do for most things in this course. And rather than moving this in a straight line along a displacement vector, we're going to move this along a curve. We want our curve to be an oriented curve. So what do we mean by an oriented curve? Well, we're going to take a pretty easy approach to this and just say, basically, if we have a curve, we're just going to choose the orientation to be a direction we travel on the curve. So just think if you have this path and you're going to walk along this path, and whichever direction you walk is the orientation of the curve. And whenever we've chosen an orientation, we refer to it as an oriented curve. So for example, we have a curve here like C. We just indicate the orientation with an arrow like this. So if we were walking along this curve, we'd start at the bottom left of the screen and walk up to the top right of the screen along the curve. And we're going to choose in the graphics that are coming up. I didn't put the little arrow on there because the graphics already have a lot going on. So just assume we have the same orientation for the curve through the rest of this pictures that are upcoming. So what we're going to do is instead of talking about moving along the whole curve, if you remember from Calc 2 or Calc 1, usually when we're setting up integrals, what we end up doing is breaking things up into small pieces and figuring out what's happening on the small piece and then adding all those pieces up. So we're going to do the same process here. We're going to take just 2 points on the curve and we're going to assume these points are close together. And we're going to approximate how much work is done in moving an object just from P1 to P2. So we can see here's 2 points, P1 and P2 on our curve. Assume that those are close together. They don't look particularly close together on this picture because I needed enough room to do the graphics, but just think of these as being quite close together. So we can think of these points P1 and P2 as given by vectors R1 and R2 from the origin. So here's our two vectors that give P1 and P2. And now we can take the vector that goes from P1 to P2, and this we'll write as the delta R1, and this is just R2 minus R1. So back from when we did vectors, we can see that this is just the difference of these two vectors to be the vector from P1 to P2. And we can see here this vector R2 minus R1, this delta R1 vector, it's not exactly the curve from P1 to P2, but it's a reasonably good approximation for it. And the closer P1 and P2 get together, the better that vector would approximate the curve. So since we can say that this is a pretty good approximation, we can say, well, the work that it would take to move along this curve from P1 to P2 is pretty well approximated by the work that it would take to move along the displacement vector from P1 to P2. So that's what we're going to do. So the work in moving from P1 to P2, we'll say this is approximated by, well, the formula we started with. So we take the vector and we're going to f of r1, so that's the force at the point P1, and we're going to dot that with our displacement vector delta r1. So this is f of r1 dot r2 minus r1. And of course, this is not exactly equal to the work in general, because that curve is not the same thing as the displacement vector, but it's a reasonable approximation. And one thing to note here is, of course, f might be changing over that curve when you go from P1 to P2, but as long as those points are pretty close together, we can say f doesn't change much over that curve, so we'll say it's approximately f of r1 over that entire segment. You could also say it's approximately f of r2, that would be fine too. We're just choosing kind of a left-hand side here, so if you think back to integrals, this is kind of a left-hand sum that we're coming up with for this. So that gives us a reasonable approximation to figuring out the work to move from P1 to P2. So now if we want to do the work along the entire curve, rather than just having 2 points, P1 and P2, we're going to put endpoints on there that break the curve up into n different intervals here, or n minus 1 intervals. And each of these points, P1 through Pn, will be given by a vector R1, R2, and so on. And so what we'll do is we'll do the same approximation on each of these little portions of the curve and add all of those up. So the total work should be approximately the sum of all of those approximate work. So for each interval, that each little piece of the curve, the work is approximately f of r1 or ri dotted with delta of ri. Here delta ri is ri plus 1 minus ri. And we add all of those up, and so we have a bunch of different displacement vectors approximating our curve. So even though our curve is not a bunch of lines, it looks like we're approximating it with a bunch of little polygons here, or with a polygon composed of these different displacement vectors. So this gives us an approximation to the total work. And if you remember back to how we developed these things in Calc 1 and Calc 2 with integrals, we should be able to guess the next step. We just want to let these points get closer and closer together so that our approximations are better and better. So the closer they're together, the closer those displacement vectors are to actually being exactly the curve. So in this case, we don't want to just take the n going to infinity. We want to take the length of the displacement vectors, the delta ri's. We want all of those, let's say, to make things simple, let's say all of the delta ri's are the same length. And we want the length of that displacement vector to go towards 0. So saying the points get closer and closer is the same thing as saying the norm of that vector, the length of the vector, delta ri, goes to 0. And that'll give me a better and better approximation to the work. So we have that the total work is given by the limit as those lengths of the displacement vectors go to 0 of that sum. And so that tells us exactly how we would calculate the work. Of course, we don't have any idea at this point how we'd actually calculate the limit of that sum like that. Kind of like how when we set up Riemann sums in Calc 1 and Calc 2, it wasn't so easy to see how we'd calculate that sum actually. But then we found shortcuts for doing it. So we're going to do the same thing here. But first, let's go ahead and give this a name. So we say the line integral of this vector field f over the curve C, and we write this as an integral, and instead of writing from A to B here, we put a C on there to indicate we're integrating over this curve, and we write f dot dr, so this is just notation, just like if you had f of x dx was just notation for the integral, and this is just this limit as the lengths of the displacement vectors go to 0 of this sum. And notice we did all of this for work here, but there's nothing in particularly important about work. It just gave us a motivation and why we would care about such an integral. But any vector field will work for this. So we can do a line integral of any vector field like this. Okay, so we motivate it so we know why we care about such an integral, at least one example of why we would care about such an integral. But the definition works for any vector field. And as I said before, even though our pictures were in 2 dimensions, all of this stuff works exactly the same if we have 3 or more dimensions. We wouldn't be able to draw a picture if it was more than 3 dimensions. We could draw pictures in 3 dimensions. They'd just be messier to look at. Or you could just pretend the pictures I gave were in 3 dimensions since I never put coordinate axes on the pictures. So we're not going to see in this video, but we'll see in our class lecture how to actually calculate these line integrals. And so what we'll do is we'll parameterize our curve C with some parameterization R of t for a less than or equal to t less than or equal to b. And when we do that, we'll be able to take our line integral and turn it into just a one-dimensional integral of the kind we saw in Calc 1 and Calc 2. But let's go ahead and give some of the basic properties of line integrals. You can see these right from the definition if you like, or you can just remember them. But we'll use these properties going forward. So let's take C to be an oriented curve and f and g vector fields defined on C. So if I take the vector field f plus g and I look at the line integral of that, it's the line integral of f plus the line integral of g. And if I take any real number a and I multiply my vector field by that to get a new vector field af, I can just pull that a out front of the line integral. So you can pull constants out of the integral just like you could with integrals from Calc 1 and Calc 2. A couple more properties here. If we have an oriented curve, C, we write negative C for that same curve, but then we're going to switch the orientation. So at the curve at the beginning of the lecture, we were starting at the bottom left and working up towards the top right. So if I took negative C, I would start at the top right and work towards the bottom left. And if we do that, if we take the line integral of f over the negative curve negative C, it just gives a negative value. So negative the line integral over the original curve C. So kind of the same way, if I, in Calc 1 or Calc 2, if I integrated from a to b, it was the same thing as negative the integral from b to a. So you just switch the direction of the interval. So same thing here, you're switching the direction of the curve. And finally, one more property. Suppose I have two curves, C1 and C2. And suppose that as I walk along C1, when I get to the end of C1, I'm at the beginning of C2. And assume they have the same orientation. So I could just make one curve that starts at the beginning of C1 and ends at the end of C2. We'll write C1 plus C2 for that curve. Then if I integrate, take the line integral over C1 plus C2, it's the same as first integrating along C1 and then integrating along C2. So those are some basic properties of our line integrals. One thing to note here is they're called line integrals, but we're not actually always just integrating over a line. We saw our curve can be curvy. It doesn't have to be a line. It's basically line integrals just because they're one-dimensional integrals, even though they're not over just regular intervals anymore. They're over curves. So again, we'll see a lot more about these and how to calculate them in the actual class lecture, but this gives some motivation for where these integrals come from and why we care about them, and then some of their basic properties we'll use.